So hello everyone, thank you all for attending to my presentation. My name is Marcel Favereau, and I am a PhD student in engineering sciences at Pontifical University, Catholic University of Chile. And today I will present our research that we have been developing with my PhD advisor, Aldo Lorca. And our presentation is entitled as Robust Streams of Forecasting, a Student's T-Mixer Vector Autoregressive Model. First of all, I want to talk about what will be the outline for today. And obviously, we will review some introduction and some motivation aspects on this presentation. For then move to some aspects in autoregressive and Gaussian mixed models. This will serve us to present our proposed model and later to review some computational experiments and their results, to finally conclude with some summary and important aspects of this presentation. And for our motivation, I want to talk about this concept of integrated management of water resources, because water resources are natural resources, and as a natural resource is not finite, and we need to manage it in a proper way in order to meet all the demands and needs over this resource. But there is a difficulty here because we are facing in Chile some water scarcity effects of climate change in the last decade. We're facing a mega drought. So obviously it's more complicated to do this integrated management. So as I told you before, there exists this management of water resources in southern Chile, where there exists a synergy in the shared use of these resources between mainly two sectors: the air power or electricity generation, and the agriculture sector. Obviously, we need to meet all the water demand from both sectors, but it is a difficult task in nature, but also because there exists some physical and regulatory constraints on both systems, so or networks. So we need to have efficient forecasting methods to know how will be the water for the future, the availability of water for the future. So what literature tells us about streamflow forecasting methods? I divided into three main groups. One of them is the forecasting with autoregressive models. And as you can see, periodic autoregressive models have been very useful in this area, with some derivation, such as exogenous variables and moving average. So autoregressive models in general have been very useful to predict some stream flows. But there is another interesting topic here, that is some research that have analyzed some modified residual process for autoregressive models, in this case of autoregressive model with students T residuals, as Christmas and Emerson did, and a very similar approach that is for a vector autoregressive model with Gaussian mixture residuals, as Calibirta, Mitz, and Sekanen did in 2016. This is important because there exists in electric power systems a model on a problem called the thermal scheduling, that consists basically in coordinate or schedules the electric plants and thermal plants in order to meet the electricity demands. So autoregressive models plays an important role here because they provide us very efficient methods or very efficient forecasting. And this has been used in robust optimization, for example, with Dashti, Conejo, Zhang, and Wang, and also in stochastic programming with Lohmann, Herring, and Rivenek. So what we are proposing here is a vector autoregressive model, but considering a mixed model for the residual process. And why we are trying to do that? Because we try to capture characteristics such as trends, seasonality, asymmetry, multiple modes in the residual process, and also the spatial-temporal correlation of stream flows. And this proposed model will be compared with a vector autoregressive model, the basic vector autoregressive model, in terms of some error metrics and the width of confidence intervals. So let's review some autoregressive models, and let's go to basics in terms of time series analysis. And you can think about a time series Y like a decomposition of a trend M, a seasonality S, and an autoregressive component X, as you can see in the respective colors here. And we are interested mainly in this last component, these autoregressive components here. And what's an autoregressive model? An autoregressive model is a linear combination of past values of the variable X in this case, plus a variable Z that is a white noise commonly assumed as a Gaussian noise. And a very similar way, you have the vector autoregressive model that is a derivation in a multidimensional way. And you have your vector of stream flows in this case will be a linear combination of the past values of these vectors plus obviously some constant and some white noise, multivariate white noise here. And it is commonly assumed that this epsilon will be a multivariate Gaussian noise, but always, as you can expect, this can capture aspects like multiple modes and asymmetry. So that's why we ask this big question, that is, can a mixture of Gaussians be a model that better represents the noise process? We're trying to answer that. So let's review some Gaussian mixture models. And Gaussian mixture models, in general, sorry, in general, they represent the distribution of a random variable X as a combination of different Gaussian distributions. And you can see it in a graphical way. Let's suppose you have this data in color, this color data, and you feed a unique Gaussian. Obviously, you are capturing all the data, but also you are capturing information that never exists, these white spaces. So if you feed a Gaussian mixed model, maybe you will capturing only the relevant information and not these white spaces. So the normal question here is how many Gaussian do we need, and what will be the parameters of these Gaussians? And these parameters are some deterministic parameters. Obviously, this coefficient pi, this vector of means mu, and these covariance matrices sigma. But this is difficult because we don't know beforehand how many Gaussians do we need. Just obviously, this is difficult to estimate. So here appears this Bayesian setup of the Gaussian mixed models, and in this case, you have these parameters are not parameters itself, but also they are latent variable. We have a probabilistic distribution over this pi, this mu, and this precision matrix of here. So computate the posterior of all of this model is very difficult in practice, and sometimes it is intractable. So we have to resort to approximation schemes. And in this case, this particular case, we use a variational expectation maximization algorithm to fit this Gaussian mixed model. And variational expectation maximization consists in an iterative way. In the E step, in the expectation step, we evaluate the posterior of distribution that we see here, the posterior of the latent variables given the observed variables. And in the maximization step, we evaluate the expectation of the probability of both the observed variables and the latent variables, but with respect to what we obtained in the E step, this posterior probability P of Z given X. Yeah. So we are interested in make some predictions. So posterior predicted density for a new value X in variational expectation maximization can be evaluated as a student's T mixture model with some parameters obtained in this iterative algorithm variational expectation maximization. But this is important because we will be considering in our vector autoregressive model later. So our proposed model is briefly it's like that. We are feeding a trend with a tail estimator that is a commonly used method in metrology forecasting. And as you can see, this TSE estimator is not affected by these groups of outliers. So that's the reason, because it's called a robust simple linear regression. And also we're considering a cosine sine model for fitting the seasonality that is also commonly used in this area. And here is our model. We are considering a natural logarithm transformation of our time series, sorry. And they are composed of a trend F, a seasonality S, and plus an autoregressive component X. And this autoregressive component is really a vector autoregressive model, but we're proposing that this T variable here have a distribution governed by a student's T mixture model. So let's review some computational experiments and what was the results. We're considering here 11 inflow points in the electric network of Chile, and that represents the 7%, only the 7% of the total locations of their electric network. And at the same time, they represent the 32% of the total water inflows of the Chilean electric network. Is an important number. So in terms of the results, we compare the Nash-Sadkiel efficiency and also the root mean square error. And you can see that we obtain an improvement of 10% with our model in terms of the NSE, the Nash-Sadkiel efficiency, and an improvement about 1.2% in terms of the root mean square error. So our model is better in that sense compared to bar model. But also, if you see the distribution of the predictions, here we are plotting the box plots of some simulations that we did, and you can see that the expected value of these simulations for both models, the bar model and our proposed model, are very, very, very similar. But if you look at the confidence intervals, bar SMM provides a trinkage of these confidence intervals as compared to bar model. And this is very important because we are obtaining here a less conservative prediction and a more exact prediction also, or forecast. So in summary, we propose a robust bar model that we call bar SMM and compare it to a bar model. Also, this bar SMM improves the NSE and the RMSE compared to bar model in a 10.3 and 1.2% respectively. Also, there exists a trade-off here about the amount of training data. If you want to capture some interesting behaviors or anomalies in the last time due to the climate change, you need to use less data to train your model. But if you use less data, the fitting or the performance of the variational expectation maximization can be altered. So there exists this trade-off between the amount of data to capture one aspect or the another aspect. So that's an important point. And in the future, we expect to extend this work to analyze some periodic vector autoregressive models in order to compare with this bar and this bar with students' T mixture vector autoregressive models. So as here some acknowledgement to our fundings, and that's my presentation for today. And thank you again for attending to this presentation. Let's review some questions or some comments that you probably have. Thank you.